So in the last video, we discussed about the partition function. We derived an expression for the partition function, right? So what was the expression for that? Qn Vt, this is for a canonical ensemble. Qn Vt is equal to sum over R exponential minus beta ER. So this was the expression for partition function of a canonical ensemble. And we discussed about the significance and the applicability of the partition function. So that is what we did. Now, in couple of videos, we will, or basically in this video, we will try to explore how this partition function can be applied to various, can be extended to various situations. So we need a connection equation. So we need a connection between the partition function and some kind of general thermodynamic parameters. Like here what we will do is that we will make a connection between the partition function and the Helmholtz free energy. So that is what we are intending to do now. So for that purpose, and also we will try, if I ask you if the partition function is an extensive property or not. So we will try to explore that part also. So our aim is to make a connection between A and the partition function. A means Helmholtz free energy and the partition function, and if this is an extensive property or not. If we can make a connection between these two, we can prove that this is an extensive property. Why? Because extensive parameter. Why? Because A is an extensive parameter. We know that. So therefore, if there is a connection, appropriate connection between A and the Qn, then we can prove that the partition function is also a extensive property. So that those are the two aims on which we are going to work. Okay. For that purpose, we take a canonical ensemble situation. Let's consider an ensemble in the, I will just keep on writing so that we can get it in the form of a note. Let's consider an ensemble in the canonical ensemble. Let's imagine that that the system is having scripted number of particles and a number of elements, right? Any ensemble system is made up of different elements. So let scripted number of elements constitute our typical system which we are taking for the consideration here. And so therefore the elements are labeled as one, two, up to scripted, right? The total energy of the system the system B, script E. You can write the script E in different forms. There are much more beautiful ways of writing it, but I'm not really good in that, so I just wrote out the script E like that. So the total energy of the system B, script E. Now we need to define the energy of the elements, right? So let ER with R is equal to 1, 0, 1, 2, up to, and it goes on. It can be anything, right? So ER is equal to, there can be any number of energy levels. There's no limitation for that. So ER represent the energy eigenvalues of the elements. Okay, so we have defined the number of elements in the system, the total energy of the system, the energy eigenvalues of each of the elements represented by ER, and okay, so for that system I can always write that if nr, small nr, represent the number of elements, with say energy ER. In that situation, I can write down sum over nr is equal to script n, right? So nr is the small nr is the number of elements with energy ER. So sum over nr should be giving you the script n. And also sum over r nr ER is equal to what? The total energy. Sum over r nr ER is equal to total energy script E, which I can write down as script n into U. So where, what is U? U is equal to E by n, which means that my U is the average energy of the element. So there are various elements in your ensemble, and U represents the average energy of the of an element of the ensemble. Okay. So U is equal to E by U, which means that it is sum over nr ER divided by n. I'm just following the equation of, let's put 1 here. Okay, sum over nr divided by n is equal to 1, and which I can write sum over nr by the script n, right? So sum over nr ER by n, which I can always write it as PR sum over r PR ER. Right? PR is the probability of having an energy ER for a particular microstate. So, and right, because U is also can be defined as sum over PR. Yeah, known as 2. Therefore, if I substitute now for the PR, if you remember the expression for the probability from the one of our past videos, like now I can write the expression for U is equal to sum over R ER into exponential minus beta ER divided by sum over R exponential minus beta ER. This is how we defined the PR, right, in the last one of our previous videos. So I can write it down like that, which can be written as equal to minus dou by dou beta ln sum over R exponential minus beta ER, right? Because this is simply our this, if I carry out this differentiation, I will obviously get this one. So I can write the U is equal to minus dou by dou beta of ln summation over R exponential minus beta R. Okay, so we will continue in the next video. I will put this equation as equation number 3. We'll continue in the next video.